Hi everybody, welcome back. We are in chapter 10 now, so we're going to start talking about parametric equations today. I mentioned in the note on the module, but if you want to have your Desmos app out and ready to go, feel free to do so. I'll be using Desmos a lot today in this discussion because we got a lot of fun kind of interactive graphs to look at. Okay, so 10.1, so defining curves via parametric equations. So consider a particle moving along a curve C. We have a lot of functions kind of at our disposal here, but they are kind of limited. Okay, we only have functions of x, functions of y, but sometimes it's impossible to describe certain types of curves using functions of x like we're used to using because they don't pass like the vertical line test, things like that. So instead of using just a traditional function of x or function of y, we can write x coordinates and y coordinates as functions of time. So typically we use the variable t for this. It doesn't have to be t, and it doesn't always have to be time either. But we can describe x and y in terms of a third variable. Okay, so in this case, that third variable is t. This is called a parameter. So t is the parameter, and we write x and y in terms of t. So we have x is f of t and y is g of t. Okay, and these are called parametric equations. So as t changes, the values of x and y are going to change. So if you look on our curve over here, right, so each value of t gives us a point x comma y. So I plug in a certain t value, it gives me an x, it gives me a y. So that's going to trace out some point on the curve, right? So this would be x comma y. That's going to be f of t comma g of t. But as t changes, these points are actually going to trace out this curve. So you'll get a point here, you'll get a point here, and this is just going to keep going and moving until it has traced out an entire curve. Okay. So parametric equation allows us to draw a lot of different types of curves. We have x and y in terms of a third variable, often called t. And this also represents motion along a curve. Okay. So let's look at an example. So sketch and identify the curve defined by these parametric equations. So we have x equals t squared minus 2t and y equals t plus 1. So if you'll see in the table over here, as the t value changes, we're going to be getting different values for x and for y, just by plugging the t value into those equations. Okay, so let's give it a try. So plug negative 2 in for x, so we get x equals 4 minus negative 4, which is 8. Plug it into the equation in y, so that's negative 2 plus 1 is negative 1. So this is going to give us a coordinate 8 comma negative 1. All right, that's the point. Point 8 comma negative 1 is the point on our curve. Okay, and you keep doing this, plug in those t values to get x and y coordinates. We're going to get 3, 0, we get 0, 1, negative 1, 2, 0, 3, 3, 4, and 8, 5. Okay, so if we want to get a rough sketch going here, so this is going to be 1, 2, 3, 4, 5, 6, 7, whoops. Let me make those a little more even. 5, 6, 7, 8, 1, 2, 3, 4, 5, negative 1, negative 1, okay. So the point 8, negative 1 is going to be down here somewhere. 3, 0, 0, 1, negative 1, 2, 0, 3, 3, 4, and 8, 5. So if we connect these dots, you can see the type of shape that we have here. So this is parabolic in nature. Okay, so we have, it's a sideways opening parabola, and each of these points correspond to a t value. So this was t equals -2. This was t equals -1. This was t equals 0. This is t equals 1. T equals 2. T equals 3. And t equals 4. Now the motion, you can see as t increases, so as t gets larger as we go down here, the points have a direction to them. It's moving along the curve in this direction. Okay, so to visualize this, let me pull up Desmos, but this is a good rough sketch of our curve. Okay, let me pull up our first example here. Okay, so there's our curve with the point. So the nice thing about Desmos is I can set it up so that the point is going to trace out the curve. Okay, so you can see actually if I turn off the curve for just a second, you can see as I let the value go from -2 up to 4 here, it's going to trace out a curve. And then of course I have it starting over. But then if you look at what curve this is, this is the curve in question, right? So it's tracing out that value because as the t value increases, the x and y coordinates are changing. Okay? And it does have a direction to it. It has motion to it, okay, as we let t increase. Okay, so that's kind of what's going on in this example. So let's just look at the next page really quick here. Alright, so using the same example, we can also place restrictions on parameters, and oftentimes that is the case, what we will do. So we're going to use the same functions, same parametric equations as the previous example, but this time t is going from 0 to 4. So when t equals 0, we saw this a little bit ago, but we get the point 0, 1. And when t equals 4, we get the point 8, 5. So that means on our graph, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5. That means we're starting when t equals 0, so we're starting at the point 0, 1. And then we're going to move along that curve until we get to the point 8, 5. Okay, so here's 0, 1, and here's 8, 5. Okay, and it would hit all the same points that it did before, but now it would just be this section of the curve, and it's still moving the same direction that it was before. Okay, so if we look on our graph on Desmos, you can see all I need to do is limit the t value. Instead of -2 to 4, just make it 0 to 4. And you can see there's our graph. And I can do the same thing to this value, 0 to 4. And you can see that it's just going to trace out this one segment of the graph now instead of the whole thing. Okay, so we can play around with the endpoints, okay, of these parametric equations. Okay, so when we are limiting the start and finish points of this parametric equation, then we have some terminology for this. So in general, the curve with parametric equations, x being a function of t, y a function of t, with t going from a to b, it has what we call an initial point at f of a comma g of a, and a terminal point at f of b comma g of b. Okay, so initial point is where it starts, terminal point is where it ends. So in the previous example here, 0, 1 would be the initial point, and 8, 5 would be the terminal point. Okay, so if we put that restriction on, then we're just kind of cutting it off at a certain point here. Okay, let's look at the next example. So what curve is represented by the following parametric equations? So we have x equals cosine t, y equals sine t, and t going from 0 to 2 pi. So if we plot a few points here, just to kind of get an idea. So plot some points. So let's pick some values that we're okay with on the interval from 0 to 2 pi. So let's try t equals 0, t equals pi over 2, t equals pi, t equals, just jump all the way up to 2 pi. Okay, if we plug those in, we get the x-coordinate first, then the y-coordinate, so cosine comma sine. So cosine of 0 is 1, sine of 0 is 0. Cosine of pi over 2 is 0, sine of pi over 2 is 1. Cosine of pi is negative 1, sine of pi is 0, and 2 pi, we have 1, 0 here. So think about these points that we just got, and think about what curve this might be that we're working with here, using these points that we have. And you can pick any values you want in between 0 and 2 pi to check this, but it looks like, so we started off, just get my values here. So we started off at 1, 0 over here, and then we went 0, 1, negative 1, 0, and then back around to 0, 1, right? If I did t is 3 pi over 2 in here, you would see we get 0, negative 1, that's down here. Okay, so hopefully you can tell what kind of shape this is, but it does look like we're tracing out the unit circle, right? So this, if I were to just kind of freehand it, it looks like it's doing something like this, right? So this appears to be the unit circle. Okay, so let's, before we keep going, let's just confirm this. Oops. I think my stylus broke. I'll grab another one. Try again. Let's see. Oh, maybe my app just froze. Oop. That's a crashed app. It can't handle all of these parametric equations. Okay, let me get this back open again. Okay, so, but what we are looking to do is to confirm that we do in fact have the unit circle here. So, and we can do this using just some of our trig identities, and actually in the process we can eliminate the variable t. So that'll actually work out pretty well for us for setting up this equation. Okay, well, I don't know what's going on with this app right now. Is it working? There we go. Okay, so we lost that stuff. Okay, so but this was just our initial point and our terminal point. Sorry about that delay, everybody. Can never count on the technology when you need it. So like I said, so hopefully you have all of this stuff. Just look back in the video. So let's go ahead and confirm that this is in fact a unit circle. So let's just take x squared plus y squared, and and do the substitution using the parametric equation. So that's going to be cosine squared t plus sine squared t. And cosine squared plus sine squared of anything is just 1. So this gives us x squared plus y squared equals 1. And this is the equation of the unit circle. Because it's centered at the origin and has a radius of 1. So let's take a look at this in Desmos. So if I get my point set up here, so here we're starting at 1, 0, and I let t go from 0 to 2 pi. This is what it does. So it looks like it is in fact tracing out that unit circle. So let me pull up the unit circle here, and then let's see. And there it goes. Okay, so notice that as t goes from 0 to 2 pi, the point, okay, so as t, put this in here, as t goes from 0 to 2 pi, the point xy, which is just cosine of t comma sine of t, traces the unit circle. So it traces the unit circle only once, moving counterclockwise. Okay, so let's look again. So as I let t go from 0 to 2 pi, notice it's moving counterclockwise, and it stops when we hit 2 pi, right, the value on the unit circle. 0 to 2 pi, so it's counterclockwise, starting at the point 1, 0, and then it hits the point 1, 0, and it stops again. Okay, so it's just one rotation around the unit circle in a counterclockwise direction. Okay, so, but now, let's look at the next example. Okay. What curve is represented by the given parametric equations? Here we have x equals sine of 2t, y equals cosine of 2t, with t going from 0 to 2 pi. So, again, let's look at that relationship. We have x squared plus y squared equals sine squared of 2t plus cosine squared of 2t. And sine squared plus cosine squared of anything is still just 1. Okay, so we still have the equation x squared plus y squared equals 1. So this still represents the unit circle. Okay, so we still have the unit circle here, but this time it's going to be a little different. Okay, so as t, but this time as t goes from 0 to 2 pi, there are going to be some different things happening, because this isn't exactly the same set of parametric equations, right? The other one was cosine t comma sine t. This one is sine of 2t comma cosine of 2t. Okay, so this time, if we check where it starts, when t is 0, we actually get the point 0, 1. So this one starts at the point 0, 1. And those 2's inside of the sine and the cosine, what they're actually doing is they're doubling the t value. As we plug in t from 0 to 2 pi, then the angles in the sine and the cosine are actually going all the way from 0 to 4 pi. So it's going to, so it goes around the circle not once, but twice. Because it's going basically twice as fast as it was before, and it goes in a clockwise direction this time. Okay, so let's take a look at that. Okay, so here's our unit circle again. Okay, so notice we're starting at the point 0, 1 this time, and as I let t go from 0 to 2 pi, notice it's moving clockwise, and it moves around the unit circle twice before it stops. Okay, so again, moves around once and twice. Okay, so one important thing to just mention when it comes to the difference between these two, because notice in both of these examples we traced the same curve, right? We traced the unit circle both times. But these parametric equations are still different. Okay? So one thing we do need to mention is, I'll put this just right down here. So note there is a difference between a curve and what we call a parametric curve. Let me elongate that. Oops. And that's a note. There we go. Okay. Just make that stand out a little bit. Nope, not going to do it. That's okay. I don't know what's going on with that. That's okay. So the difference between a curve and a parametric curve has to do with that motion. So like we said, both of these sets of parametric equations traced the same curve, right? It traced the unit circle both times. But the parametric equations were different. The parametric curve describes not only what the shape looks like, but how like a particle would move, right? How the curve is changing, how it's moving. So whether we circled it clockwise or counterclockwise, whether we circled it once or twice, right, or 100 times, whatever the case may be. So we need to distinguish between a curve and a parametric curve, because even though they might look the same, one of them gives us more information. Okay, so let's look at another one. So sketch the curve with parametric equations x equals sine of t, y equals sine squared of t. Okay, so let's make a note of something here. So notice, oops, if we're trying to determine what type of shape this has without just plotting it, we can look at the relationship between x and y. In this case, y equals sine squared, sine squared of t, okay, which is just another way of writing sine of t quantity squared, and sine of t equals x, so this equals x squared. So what this means is the point xy that we're working with here moves along the graph, right, the parabola y equals x squared. But it's not going to move along the entire parabola. It's not just the whole parabola, y equals x squared. It's only a piece of it. And the reason for that is because the function sine here, in both of those, sine oscillates between the values of -1 and 1. So sine will not grow infinitely large. It will only have outputs between -1 and 1. So since sine of t is between -1 and 1, we only trace the parts where, so x is sine of t, so that means x has to be between -1 and 1, right? Because that's what our parametric equation tells us. Okay. So we trace the curve. We're going to be tracing it infinitely back and forth. So it's not just going to go once and then stop. The reason for that is because sine not only goes between -1 and 1, but it oscillates. It actually does keep going forever, but it only goes between those two values. So because sine of t oscillates. Okay. So let's take a look at this one. Okay. So here's our, perfect. So here's our curve, this parabolic, going between x equals -1 and 1. Okay, so then as t goes from 0 to 2 pi, notice what happens. Goes up, and then down, and then back, and forth. So one period, one factor of 0 to 2 pi, makes it go back and forth once on the curve. And then if you just let that keep going, right, as sine continues to oscillate, then it's just going to keep going back and forth on this same curve. Okay, so this is the curve that we're tracing just from -1 to 1 along this parabola. Okay, so, and that's again the difference between like the curve and the parametric curve. The parametric curve is one that's being constantly traced out multiple times over this parabola. Okay, so let's go back here. So in general, so a piece of information for us here, in general, if we need to graph an equation of the form y equals f of x, so if we have just a regular old function, but for some reason we need to put it into a parametric form, we can do that. All we need to do is let x equal t, so let x basically just be the parameter, and then y is f of t. Okay, so if we want to graph a regular function using parametric equations, we can just let x be the parameter, right? X equal t, and then y equals f of t. Similarly, if you want to graph a function in the form in terms of y, you just let y be the parameter, so y equals t, and then x is a function of t. And that would give you a function in terms of y. Okay. Now, one of the things that is very interesting, I think parametric equations are a lot of fun to work with because you can draw all sorts of things with parametric equations. So I want to show you a couple on Desmos because the book just does want me to emphasize the use of technology here. So Desmos is able to make all sorts of parametric equations that can do all sorts of crazy things. There really is no bounds, no limits on what you can make with parametric equations. Let me just show you a couple here. Okay, pull open my extra graphs here. So let me, this is going to turn all of them on. Yeah, so ignore all these other ones for just a sec. We'll come back to those. Okay, here's the first one. So let me zoom out so you can see. Here's a piece of it. Okay, so this is a parametric equation using just a simple combination of t's and sine of t's. So if I let my point trace out the curve, you can see what it's doing, right? So it's moving along very quickly there, tracing out the whole curve. But this is basically what we're doing. And there's a lot of computational significance to this from a technological standpoint. This is how we can tell computers how to draw things, how to graph things, is by setting up a system of parametric equations and then telling the computer where the parameter is going to and from. And then you can use that to draw things. You'll see when you get to Calc 3 as well, we can use these to draw things in 3D. That would be like what a 3D printer does. So there's one. Turn that one off. The one that's a little smaller here. Zoom that in. So here's kind of an interesting looking one. We got this weird like quilt shaped one, and then if I let the point just start to move, notice this one's moving really fast. It's booking it. You can't even really see a distinction where the point is moving. One thing that Desmos can do that I like is it allows you to slow it down. So I'm going to start slowing it down a bit. We're at half speed. Even now, you can start to see it. Slow it down a little bit more, a little bit more. There we go. So now you can really see where the point is moving. You can follow it as it's tracing around and around on this curve. Okay, yeah, and you can just keep watching this, right? So you can trace curves, very complicated curves like this, which this type of curve, no way we could describe that with a function of x and y, right? There's no way this is a function. It doesn't pass vertical line test, horizontal line test, any type of line test you got. Okay, and let me show one more. Oops. So something a little more kind of like a spirograph, if you guys are familiar with what that is. So this is again just combinations of sines and cosines here. Nothing really that different, but so notice this one's moving even faster, right, as we go around. So let me slow this one down a bit. Slow this down even more. So you can start to see that shape, but again, it's just starting to look like it's kind of hitting those points, but now we can really start to see how it's tracing along each of those parts of the curve. And it is one smooth flowing curve the whole way. So very, very interesting to kind of play around with these parametric equations. I think it's a lot of fun just to be able to play around with them and see kind of what you get. You can make all sorts of kinds of different drawings and shapes with these. So, okay, let's go back to the notes. Let's look at the last page. Okay, so we're going to talk about one specific type of parametric equation that is very famous, I guess you could say, and that's the cycloid. Okay, so the cycloid has a pretty rich history, tying back to some very famous mathematicians, including Galileo was one of the first people to really study the cycloid. But basically what the cycloid does is it takes a point on a circle, and you start rotating and rolling the circle, right? If you picture like a wheel, rolling the wheel down the x-axis, and then you trace out a shape with this circle. So let me get my cycloid going here. So I'm going to start it at 0. Zoom this out a bit. So I have it set to do a few here. Okay, so you start rolling that wheel, and that point starts tracing out a curve, okay, as you're going along. And now it's coming back, but it would traditionally just go in one direction as a parametric equation. Okay, but you're tracing out this curve, and it does have a lot of practical applications. It also has some like architectural applications as well. That's what Galileo actually wanted to use it for, was to build bridges. So very, very interesting shape to work with. But what we're going to be doing with it is finding and determining the parametric equations for the cycloid. Okay, so let me turn that off. Okay, now this is not something I would expect you to be able to come up with on your own necessarily. The cycloid is pretty complicated, but this is just so you can see kind of how we're finding these in this case, because this one is a little more well known. So we have a circle that has radius r, rolls along the x-axis beginning at the origin, and we're going to determine the parametric equations for the cycloid. So a couple things that you're going to have to just kind of go with me on here. So first of all, this segment OT down here, the length of that segment is going to be the arc length of PT. So PT is the curve around the circle here. Okay, so this is PT that we're looking at, and these two are going to have the same arc length. That's a bit of geometry actually, because this length you can see there in the diagram is r times theta, where theta is this angle of rotation here in the circle, and r of course is the radius. But this is actually a little more geometry than what we're doing right now, so you don't really need to worry too much about that. That's just some geometry. So we can identify the center of the circle. So the center of the circle is, if we go over this many units and up, right, up a factor of r, so that center is going to be r theta comma r. Okay. And we're going to let P be just an arbitrary point x comma y. Right? This is the point that we're going to be using to trace the parametric curve. So then the length of x, so x is going to be, right, this is the x value of P, again that's P, and then this is the y value of P. So the x value is just going to be this segment OT minus this portion, right, PQ. So we take the whole thing minus part, and we're left with x. So this is going to be the length of OT minus the length of PQ. So that's going to be r theta minus the length of PQ you can determine using trigonometry, right? Because again, you have that angle theta here. So that would be, right, theta opposite, and we already know the hypotenuse side is r. So opposite over hypotenuse, that would be sine. So sine of theta equals PQ over r. So PQ is r sine theta. Okay, so a little bit of trig there. So again, if you want to look a little more closely at this, if that's theta, this is PQ, and that's r. So sine of theta equals PQ over r. So PQ equals r sine of theta. Okay, so just a little bit of side work there. Okay. And then you can go ahead and factor out an r, just to condense a little bit. So r times theta minus sine theta, that's going to be our x value. And then the y value is going to be the same length as TQ, right? So it's going to be this whole piece minus this piece. Okay, so we're going to take the whole thing and subtract off the smaller part. So that's going to be TC minus QC. Right? So TC, that whole segment there, that's just R. And then minus QC, this we can find again using trigonometry. This time we'll use adjacent over hypotenuse, which is cosine. So that gives us minus R cosine theta. Okay, and then factor out the r, you get r times 1 minus cosine theta. So therefore, the parametric equations of the cycloid are x equals r times theta minus sine theta, and y equals r times 1 minus cosine of theta. Oops. Here's I've run out of space down here. There we go. So 1 minus cosine theta in there. So those would be our parametric equations for the cycloid. So not necessarily intuitive, right, by any means, but we were able to find them just using a little bit of trigonometry, tiny bit of geometry, and just our understanding of lengths and angles there. So just a brief note, each arch of that cycloid comes from one rotation of the circle. So you can see that back here on Desmos. Right, if I take my cycloid and I adjust it so it's only going, right now I have it going to 6 pi, but if I only do it to 2 pi, and then I let it run. So 0 to 2 pi makes one arch. And then it's coming back there. So each arch is consistent with one rotation of the circle. Okay, so one t going, or theta going from 0 to 2 pi. So we're using theta as our parameter in this case instead of t. Okay. All right, so that's it for the cycloid. And that is our introduction into the study of parametric equations. I think a really, really fun and interesting topic that has a lot of uses that we can work with, especially when it comes to graphing and doing things using like modeling and stuff like that. So that's it for section 10.1, and I will see you all